Our next application of network flow will be the Min-Vertex cover problem. And in the Min-Vertex cover problem, you are given an undirected graph, and you want to determine the size of the minimum subset of nodes such that for every edge in that graph, at least one of its endpoints is a node in that subset. So for example, I've demonstrated this with the graph on the screen. If we mark the 4 kind of middle blue nodes, we can see that every edge in the graph is adjacent or connected to at least one of those marked nodes. You can kind of reason about and notice that there's no set of 3 nodes that would be able to cover every edge. And so we know that the size of the min-vertex cover for this graph is 4. To solve this problem on a constricted graph like a tree, we can use a greedy or dynamic programming approach to solve it in linear time. On a general graph, this problem actually is very difficult and is a NP-complete problem with no known polynomial solution. But in kind of the middle, we have bipartite graphs, which we can actually use flow and reduce our problem to bipartite matching. It turns out that due to Koenig's theorem, we actually know that the cardinality of the min-vertex cover is actually the same as the cardinality of the maximum matching in bipartite graphs. So it is sufficient to take your bipartite graph that you are trying to get the min-vertex cover of and solve the same bipartite matching problem on our induced flow graph that we've already previously discussed. And here we can see the graph that would be induced.